My name is Mitch Savali, and I am enrolled in Physics 2211. This is Lab 2, Motion of a Falling Object. So the purpose of this lab is to measure an object's motion after it is dropped from rest at some height, and then at the end of the lab, I will compare my observed data with two computational models. The computational model that took gravity and drag into account was much more similar to my observed results than the computational model that only took gravity into account. A couple of the fundamental principles that we used are Newton's second law, which states that the acceleration of an object is dependent on the net force acting upon the object and the mass of the object. Newton's second law also includes the momentum principle, which can be used to derive the velocity and position update formulas. We use Newton's second law here because we need to find the net force acting on an object by summing its forces from interactions with other objects. Later in this experiment, we will also see that the object is affected by a non-zero acceleration, which relates to the momentum principle. Another principle we use is the formula for gravitational force, which you see here. Since our object is falling towards the ground, we know it's affected by gravity. Finally, we also use the formula for drag force, which is an opposing force to gravity, which results when the object interacts with the fluid air. The greater surface area of an object, the greater drag force. We know that the drag force is affecting the object in the experiment as our object falls somewhat slowly. For the video, we use a paper ball, which is the system, and the surroundings is everything else. I positioned my coordinate plane with the positive y-axis going up and the positive x-axis going to the right, so my model moved along the negative y-axis. I used my ruler as the scale calibration. My initial conditions are shown here, and you can see the y-graph is exponentially moving into negative direction due to the acceleration of gravity on the object. For the computational model that only took into account the force of gravity, I plugged in the initial conditions I mentioned in the previous slide and had the proportionality constant set to 0. Sorry. The net force will only be the force of gravity, as you can see in line 70. Then using the velocity update formula, I calculate the ball's final velocity and use that to calculate the ball's final position in the position update formula. For the computational model that took into account the force of gravity and drag, I have almost the same code as the previous slide. Some changes are the proportionality constant, which I found by trying different numbers until the endpoint of the model was about the same as my observed data. Also, I have the formula for drag force here, which is combined with the force of gravity to find net force. Here's the data from the two computational models. The observed data on one graph, you notice how the computational model that include drag more closely models what we see in the real world. However, the middle of the graph does have some discrepancy. This could be because of human error when positioning the center of the ball in the tracker, as the ball was blurry during some frames. It could also be from how I did this experiment a little too close to the AC unit, which is blowing wind. It could also be from how the ball could have slightly turned as it fell, which meant that the B value and the drag force formula was not constant like I had assumed because the paper ball was not completely smooth. Also notice how the gravity-only model displays the object at a much further position compared to the models that include the drag force at the same time. Remember that this is because drag is opposing gravity, so the object's force in real life going downwards is smaller and it is falling at a slower rate, so it does not move as far in the same amount of time. For what does this mean, we can see that the model that considers gravity and drag will reach a terminal velocity. This is because it looks like towards the end of the velocity, it becomes constant, which indicates that zero change of velocity, which means zero acceleration and zero net force. We have no net force here because the forces of gravity and drag cancel out. For the what-if question, the object's terminal velocity is still the same if it had an initial velocity in the y direction. The only difference here is that the terminal velocity is reached more quickly compared to if the ball is dropped from rest. So to conclude this lab, we use Newton's